Math 2414, other convergence tests, integral test. Yep. All right, so here come a bunch of tests to answer the question, does a series converge? So far, we've seen a very few limited options. If we have a closed form for the partial sum, then we can see if that sequence converges by taking the limit and approaches infinity. If our series is a geometric series, then we can simply look at the ratio. If its absolute value is less than 1, then the series converges, otherwise it diverges. If we happen across a telescoping series, then we can analyze convergence by finding the telescoping form of the partial sum. Remember, telescoping is when you add a bunch of terms and you get a bunch of cancellation, leaving a finite number of beginning and ending terms. Then you just take the limit. We've also looked at harmonic series, whose sequence is the reciprocal of an arithmetic series, and harmonic series always diverge. But those are very limited in scope, so we need some other tools to answer the question, does this series converge? The integral test is pretty straightforward. Under the right conditions, simply calculate an improper integral, and whether or not this series converges hinges on whether or not the integral converges. Specifically, if a function, we'll say the function is called f of x, is continuous, meaning no breaks in the graph, eventually positive. Now this is a little bit more specific than what the book says. We'll talk about what it means to be eventually positive in a moment. And eventually decreasing. But if your function is a continuous, eventually positive, eventually decreasing function, and your sequence that you're taking the sum of is defined by an equals f of n, where n equals 1, 2, 3, or wherever it begins, because series don't have to start at 1, then, and here comes the key part, the sum from 1 to infinity of the nth term, I wanted that to be yellow, are we good now? Then the sum converges if and only if the improper integral from 1 to infinity of the function, or wherever the sum begins, it doesn't have to start at 1, converges. So we can check convergence or divergence of the sequence by checking convergence or divergence of the improper integral. What I mean by eventually positive is you may have a function that starts out positive, negative, or 0, but at some point it becomes positive and stays positive. Technically speaking, it's eventually positive. It's eventually positive if there's some number n such that f of x is greater than n for every number greater than n. So there's a boundary beyond which your function becomes and remains positive. And eventually decreasing is kind of the same thing, that there's some n such that your function is decreasing on the interval n to infinity. In other words, once we cross n on the number line, my function is decreasing, or my function is decreasing. All right, so the trickiest part about the integral test is verifying that your function satisfies all three conditions. The continuity is usually pretty easy to spot. Our discontinuities are usually located where denominators are equal to 0 or where things are undefined. Eventually decreasing and eventually positive, sometimes they're clear and sometimes they aren't. We'll look at a couple of examples. For example, we're going to verify that the integral test applies to the following series and use the integral test to determine if the series converges. So before you jump into integrating anything, you need to first identify what your function is and see if it satisfies all three criteria. We're looking at the function f of x equals natural log of x over x, and we're looking at this on the interval 1 to infinity since our sum starts at 1. Which reminds me, and I meant to fix this before we started, but all these things up here about being continuous, eventually positive, and eventually decreasing, that needs to be on the interval 1 to infinity or wherever your sum begins, because that's the interval over which we're going to calculate the improper integral. But I digress. Our function is f of x equals natural log of x over x, which is easy to extract from the argument of the sum. And we're going on the interval 1 to infinity because that's the discrete interval over which we're taking the sum. All right, so let's start with continuity. Let's go ahead and type this. Continuity. We do have a natural log, so we have to be careful of that. We know that the natural log of x is continuous for x greater than 0, meaning that we can't take natural log of 0 or negative numbers and keep things real. Spoiler alert, you can take logs of negative numbers, but you get complex solutions for complex values. But the natural log is continuous as long as x is positive, but since we're integrating over the interval 1 to infinity, then x is always positive. Let's see. But we also have a denominator we need to be wary of. Have the text box, please. And f of x is, well, let's just say that f of x is discontinuous at x equals 0 because of the denominator. But again, that's not going to be a problem for us because we're only integrating over the interval 1 to infinity. So our function does satisfy the continuity requirement on the desired interval. But what about the positive and decreasing aspect? Well, if we were to look at the graph of natural log of x over x, actually we don't even need to do that to determine if it's positive or not. Next, please, thank you. Okay, so let's say eventually positive. Clearly, x is greater than 0 on 1 comma infinity, and I'm just going to type the interval like that, so I have to switch back to drawing. Also, the natural log of x equals 0, excuse me, natural log of 1 is equal to 0, but after that, natural log of x is greater than 0. And if you weren't sure about that, then you should know what the graph of natural log looks like. Specifically, if you wanted to look at the graph of natural log, it has a vertical asymptote on the x-axis, excuse me, the y-axis, starts out low, the asymptote crosses the x-axis at 1, and then does a very slow rise. So our function isn't positive at x equals 1, but beyond that, it is positive. So this function is eventually positive. So we're okay in terms of the function being positive at some point. As far as eventually decreasing, oh, by the way, the graph I drew was just for the numerator of the function. So this thing is eventually positive on this interval. This thing is always positive on this interval. And of course, the ratio of two positive numbers is positive. So I want to be clear that even though we were looking at the graph of natural log of x, we were looking at it as part of a bigger function, the natural log of x over x. All right, so let's get back to the eventually decreasing. Now, some functions are clearly decreasing. This I would not say is one of them. But luckily, we have a Calculus 1 tool to answer the question, is this function decreasing? We can check to see if the derivative is negative, and we'll say eventually, because again, our function doesn't have to be decreasing right out the gate. It can go up a little bit, it can even waver some, but at some point it has to start to trend down and not turn back up in order to be called eventually. All right, so we've got to do a little bit of Calculus 1. I'm going to go to the next page. We're going to take the derivative of this, figure out when it's positive and negative. So you may not have seen this for a while, but you know, you're in Calculus 2, and as I've mentioned more than once, all past math is fair game. All right, so let's calculate the derivative of natural log of x over x. Quotient rule. The bottom times the derivative of the top. So x times 1 over x minus the top times the derivative of the bottom. The derivative of the bottom is 1. The bottom squared. And if we clean that up, we're going to get 1 minus the natural log of x over x squared. All right, so let's think about that. Let's think about that derivative for a second. want to know when it's positive or negative. Remember, we're only looking on the interval 1 to infinity. So clearly, the denominator is going to be positive because it's x squared and x isn't 0. But as far as the numerator, if we want our function to be decreasing, we need this function to be less than 0 at some point. So this function will be less than 0 when its numerator is less than 0, because the denominator is always positive. But this is the same as saying when the natural log of x is greater than 1. So we can figure out when that happens, and if that happens somewhere inside of our interval, eventually and forever, then we're okay. So let's take a look at natural log of x greater than 1. Now, I don't know how you were taught to solve inequalities, but when I teach college algebra, I teach a technique that always works. The first thing you do is pretend that it says equals. So let's pretend it says equals. Solve that. To solve an exponential, you just rewrite this in to solve a logarithmic equation like this, you just rewrite it in exponential form. Remembering that the answer to a log, in this case 1, is the power that turns the base, and in natural log, the implied base is e, to the argument. So we get x equals e. But that's the solution to this equation, and so we use that solution to partition the function's domain. We are only looking at 1 to infinity. So we use this to partition. This partition, what doesn't, but it kind of does now. The domain that we're looking at, we're going to partition this at e. So 1 to e, and then e to infinity. And then when we pick a test value from each one, put it back into the inequality, see if it makes it true or false. If we pick, go with green. If we pick x equals 1 from this interval, and x equals, we'll say 3, we tested natural log of 1 to see if it's greater than 1, that would be false. The log of 1 is 0. But if we looked at natural log of 3 greater than 1, I don't know the natural log of 3, but I know the natural log of e is 1, and I know that natural log is an increasing function. But you could get out a calculator and verify that natural log of 3 is greater than 1. Although honestly, since 3 is greater than e, remember e is about 2.72. I'm assuming you remember that, but in case you don't, now you do. But yeah, the numbers in the second interval, or a test value from the second interval, made the inequality true. And so that means that the inequality is true on that entire interval that the 3 came from. So the conclusion that we can draw here, we'll put this in blue, therefore, natural log of x greater than 1 on the interval e to infinity. But what does that mean in the context of showing that the function is decreasing? Well, our function is decreasing when the natural log of x is greater than 1. Or rather, I should say our derivative is negative, which means our function is decreasing. So, to put all that together, we'll type this. Since natural log of x is greater than 1 on the interval e to infinity, then 1 minus the natural log of x is less than 0 on e to infinity, which means that the derivative is less than 0 on to infinity. And again, those e to infinities are just intervals. I'm typing the word infinity. But what this does, this shows that the function is eventually decreasing. Now, like I said, the hardest part about this sometimes is showing that the function is eventually decreasing by showing that its derivative at some point becomes negative and stays negative. And this point is eventually decreasing once you pass the number e. So once you hit 3, 4, 5, and so on, our function is decreasing. But we've only verified that we can do the integral test, because the integral test requires 3 criteria: continuity, eventually positive, and eventually decreasing. But we've shown that it satisfies all 3. So now we can compare, we can check the convergence of the series by checking the convergence of the integral. So we're not out of the woods yet. Now we need to do the integral. this, please. So we need to find the integral from 1 to infinity of the natural log of x over x dx. And we'll do that on the next page. Integral 1 to infinity, natural log of x over x. Don't want to spend a whole lot of time reviewing how to do integrals, because at this point I just have to assume that you know. I will tell you that this is a u substitution. We're going to let u equal the natural log of x. And the reason we're going to do that is that because the derivative of natural log of x is 1 over x, which is already present inside the integrand, so we can make the du package. Also, x equals 1 implies u equals 0 because the natural log of 1 is 0. And x approaches infinity implies that u approaches infinity, because the graph of natural log, once again, is a slow but steady increase to infinity. All right, so this means that our integral is now equal to the following. 0 to infinity of the natural log of x becomes u, and the x, the over x and the dx becomes du. Again, don't lose sight of the du package. It's right here. All that becomes du. This is a very easy integral to integrate. I am going to do it the proper way, which is to replace the infinity with the t, and then integrate the function from 0 to t. The function's easy to integrate. 1/2 u squared from 0 to t. And because I changed the limits of integration, I don't have to change this back to x's. I can just attack it right now. So this is equal to the limit as t approaches infinity. I substitute the upper limit, I get 1/2 t squared. Minus, and if I substitute the lower limit, I get 1/2 0 squared. Of course, that's 0. But what happens to, well, that's 0. What happens to this as the t approaches infinity? This approaches infinity as well. You square infinity, it's still infinity, and if you take half of that, it's still infinity. So what does this mean? Well, the integral just diverged. That means that the series diverges. Let's wrap up this example in this video. Since the improper integral diverges, we conclude, I can type, that the series also diverges by the integral test. All right, so as you can tell, the integral test can get hung up in a couple of places. Number one, verifying that the function satisfies the 3 criteria. Continuity, that's usually easy to figure out. Eventually positive, sometimes obvious, sometimes not, and eventually decreasing. Some functions are obviously decreasing. The one we had wasn't, so we had to check its first derivative to see if it became negative. All right, so that's the end of this video. In the next one, we'll take a look at another example of an integral. This one will be a lot